Hello everyone and welcome you all again in this class, and here we are going to discuss some of the numerical problems. So in the previous class we have discussed different types of sections that depends on the actual depth of neutral axis, and when we compare the actual depth with the maximum or limiting depth, then we are able to categorize our section into three categories, that is balance section when xu is equal to xu maximum, or under reinforced section when xu is less than xu maximum, and as over reinforced section when the xu is greater than xu maximum. So this is the simplified diagram of all the strain profiles of the three different cross sections. So the same thing we have written here in the balance sections and the under reinforced sections, and we have discussed all this theory in the previous video also. So you all can go through that and learn how to calculate the moment of resistance in different cases. So basically we want our design to be under reinforced and we try to avoid the over reinforced design. So basically in RCC there are two type of problem. The first type is the analysis problem, and here we are asked to calculate the moment of resistance. देखिए मोमेंट ऑफ रेजिस्टेंस बार बार क्यों पूछा जा रहा है, क्योंकि मोमेंट ऑफ रेजिस्टेंस बीम की कैपेसिटी है. And in the analysis problem we are given all the data like the cross sectional dimensions and the grade of steel and concrete, and the area of steel is provided with the clear cover, and then we have to calculate the capacity of the beam, how much load, how much bending moment the beam as a flexural member can resist. So these types of problems are the analysis problem, and here in the first step we have to first of all calculate the value of xu maximum, and we all know the value of xu maximum only depends on what effective depth d and grade of steel fy. And we can remember all these three values of xu maximum, or also it is given in the IS code. So here if we know the grade of steel Fe and we know the effective depth, then we can very easily calculate what is xu maximum for any cross section. Whatever may be the dimension, whatever may be the area of steel, whatever may be the grade of concrete, it doesn't matter. The value of xu max remains same for the same value of d and fy. After calculating xu maximum, in the next step we have to find out the actual depth of neutral axis, and that depth is represented by xu. And the basic fundamental of calculating xu is equating the tensile force and the compressive force, and we can easily do this and ultimately get the value of actual depth of neutral axis. Now in these formula you have to put the values of Fy, Fck, Ast and B in terms of Newton and millimeter. Okay, if the design strengths are given in megapascal, then you can easily convert them into Newton per mm square, and the values of dimension of the beams and the area of a steel has to be taken in millimeter or millimeter square. Alright, and then you will get the value of xu or xu maximum in terms of millimeter. So this is very important point, please note it down. After calculating the value of xu and xu limiting, we have to do a comparison. If in case by chance xu comes to be equal to xu limiting, then such a section is said to be balance section, and it is very rare to obtain. Okay, so in balance section we can directly use the value of xu limiting for calculating moment of resistance. If in case the value of xu is less than the xu limiting, our section will be under reinforced section, and in that case we just have to use the value of xu only to calculate the moment of resistance. Alright, if in case the value of xu exceeds the value of xu limiting, then that section is said to be over reinforced section, and such section we try to avoid in our design cases, and we just have to use the value of xu limiting only, because the xu cannot go beyond xu limiting to calculate moment of resistance, and the value of ultimate moment of resistance in over reinforced beam remains limited to the value of mu limiting, which we calculate with the help of xu lim only. And here we use the formula from the compression side only, as the steel has not yielded. So the last step comes, that is to calculate the moment of resistance. And moment of resistance, this is the celebrated formula from the compression side, and this is the formula from the tension side. Okay, so this is very clear, and you can choose whatever is suitable, comfortable or easier for you. All right, the answer will be same from both the formula. All right, but here we have to use the value of XU as we have discussed in step 3. So this should be very clear to you. At the end of this video, we will also discuss one case of under reinforced beam and one case of over reinforced beam, and we will calculate the moment of resistance in both of the cases. But before going to that, I would also like to discuss the second type of problem, which is generally also asked in RCC problem, but this is not in our syllabus. This type of problem is said to be the design problems. In this case, we have to design the members. In this case, the external loading conditions are given and we have to design the individual components. So in our case, we can think of design of beams as flexural member. But of course, in such problems also, the span length is the distance between the two ends or the supports of the beam will be given to you. And from the span length, you can easily get the value of gross depth of beam. And it is generally taken as the 1/10th or the 1/12th of the span length of the beam. And since the loading conditions are given, so we just make the load factored load. Factored load कैसे बनाते हैं? 1.5 से multiply करते हैं. So generally the loading is in UDL format, uniformly distributed load. And from this factored load, we can also calculate the maximum moment that is going to act on the cross section. And depending on the components, environment and site condition, we can choose the value of FCK and the grade of a steel, and then we do the designing of the beam to ultimately get the value of total area of steel reinforcement. And after getting AST, we provide the reinforcement bars in the cross section of the beam. So the same thing is written here. WU is the factored load, and factored load is equal to 1.5 times the working load. And if MU is not given, then for simply supported beam loaded with UDL, MU occurs at the mid span. And I hope you must have remembered this formula which we have proved a year back. MU is equal to WU L square by 8. This is the maximum moment that acts at the center of the beam. So this formula again comes in the role of design here also. So we always design for balanced type of section, where moment of resistance is equated with this formula, and then we equate this moment of resistance with this value of maximum moment. Here it is written mu is equal to moment of resistance that we have calculated here, and the same thing is done here. WUL square by 8 is equated with this formula, and in this equation if you see, everything is given: WU, span length, grade of steel and XU limit. And this equation will give us the value of effective depth D. And in the next step, we can calculate the area of steel reinforcement by equating the total compressive force equal to the total tensile force. And we can see the same thing is done here, and here only AST is unknown, so this can be also obtained very easily. So I'm not going to ask much from the design problems. Basically we will try to focus on the type 1 problem only, because our syllabus is limited up to the analysis of singly reinforced beam. So this is one of the example of type 1 problem. Here in this case, if you see, the dimension of the beam is given. What it is? 300 mm into 200 mm. So here effective depth directly is given as 300 mm, and the grade of steel used as Fe415. So we can easily calculate XU limiting, as the first step says, is equal to 0.48 times D, which is equal to 300 mm for Fe415, and we can get the value of XU limiting. After this, we will also calculate the actual depth of neutral axis, and we just use this formula. And here we have used all the values in terms of Newton per mm square or millimeter square, and then we get the value of XU actual equal to 90 mm. Now many of you must be wondering, how is this AST calculated? So in this formula we have used the value of AST is equal to 452 mm square. How it is obtained? This is written here. Since we have provided 4 bars of 12 mm diameter, you can remember this is the notation of providing steel reinforcement in the beam. I hope this notation you must have studied in working stress method also. So 4 here represents the number of bars, 12 here represents the diameter of bars, and 5 is the notation for the diameter. So total area of steel reinforcement provided is equal to 4 times pi d square by 4, and d is equal to 12, and we can easily get the value of AST, and the same value is used in this formula. So after calculating XU limiting and XU actual, we can easily observe that XU is less than XU limiting. So our section is under reinforced section, and it is very easy to calculate the moment of resistance, and we can calculate the moment of resistance using this formula. And here we have to use the value of XU equal to 90 mm that we have calculated here, not the value of XU limiting. Okay, in that case XU is equal to 90 mm, and if you do this you can easily arrive to the moment of resistance. Is it clear to you? And you can always convert it into the kilonewton per meter. And now for your reference, I have also put here a type 2 problem. So if you look in this problem, we are not given the area of steel reinforcement. Rest everything is given here. The effective depth, width of the section, grade of steel and concrete. So how to calculate this area of steel reinforcement? So just like in the previous case, the first step will be to calculate the XU lim, and after this we also calculate the limiting moment of resistance, and we just use this value of XU limiting in this equation, and we have arrived to the value of MOR lim. And the next step will be to equate the compressive force equal to tensile force, and then here you can obtain the value of area of steel, because this is the only thing which is unknown here. When we get the value of area of steel is equal to 474 mm square, now it depends on us that which diameter of bars we are going to choose. So I have taken 2 bars of 12 mm and 2 bars of 14 mm. So the total area that we get from these bars must exceed the value of AST limiting, and I just provide these bars at the bottom of the beam, since this is a singly reinforced beam.